Welcome to this workshop on adaptive tuning. In this workshop, we'll look at how adaptive control can be applied to a nonlinear process to improve control capability. For this workshop, we'll be using a flow loop in which the install characteristics of the valve are very nonlinear. At the first part of our workshop, we'll look at the interface for adaptive tuning and look at this nonlinear flow loop operating over a wide operating region. We'll then look at how the adaptive control has automatically identified the models of the process based upon set point changes. We'll then look at how the models that were identified are then applied to adaptive control. And last, we'll turn on adaptive control and just see the improvement that this makes in the control over a wide operating region. The process that we'll be using for this example is just a flow loop where the valve has a nonlinear install characteristics. And this is pretty common. Oftentimes nonlinearities can be introduced by other things within the process, but this is a simple example to illustrate this problem. So for this workshop then, we will then go to our tune application, which supports both demand and adaptive tuning, and look at our flow loop. So we'll select the flow loop. And in this particular case, we notice that this flow loop is indicated as having a high degree of oscillation. So this is one of the indications that possibly you have a nonlinear install characteristic. As we see here in the trend of the PV and set point, we notice that in one operating region there's very sluggish response, but in other areas where the gain is higher, you see a very oscillatory type of response to a set point change. This is also reflected in the valve itself, and so this is very characteristic of a nonlinear application. With adaptive capability, we're automatically identifying the process model each time there's a set point change in automatic or a manual change in manual in the valve position. As soon as a change is made, we'll notice that this trigger changes to indicate that a set point change or output change in manual has been detected. At the point of the trigger then, we will then be collecting in the controller itself each execution. As we see here, it now has been triggered by the set point change, so that information is now being collected at the controller. And within the controller, we automatically identify the model. So this is all contained within the controller, so that there's no skewing of the dynamics that are identified by communication or anything else. So a very clean way to identify the process here. So in this particular case, then we'll look at how this information that we collect then is used in terms of improving the control. So in this particular case, then we have identified a number of models. This process has been running for a period of time with adaptive turned on. And as you can see here, our model gain is changing all the way from 0.3 all the way up to 1.1. So over a factor of 3 change in the process gain from operating in the high end of the valve to the low end of the valve. So we can look at how the gain is changing as a function of the thing that's causing this gain change. So the gain is changing as a function of the valve position, which is implied by our output of our controller. So in this particular case, the driving force is the output. So we identify that as our state parameter. By requesting plot all, then all the models have been identified are then plotted as a function of valve position. As we can see in the upper region of the valve, the gain is quite a bit lower than in the upper region. This particular adaptive control identifies not only the gain change, but also any change in time constant or dead time. And so it's a very general capability that can handle all sorts of nonlinearities, changes in dead time as well as gain or time constant. Based upon the models that were identified, then we can then break up the state perimeter into a number of regions, up to 5 in this particular case. And then what happens is that the identified model in each region, that is the average of the different models that were identified, are then automatically used to determine the tuning at any point in time. By turning on the partial adaptation, then as the state perimeter changes from one region to the next, we automatically start using the next identified approved model for that region. And then we control in that way. The tuning is based upon the model as well as the tuning method that you've specified, and that then determines the tuning at any point in time. In this case, it's called the working gain, reset, and rate, so this will be changing as we go from one region to the other. By doing this, then, we can always provide best control at any point in the operation of our process. So to see the impact of this tuning, we'll have to look at the operation over a period of time. And but we can start to see that as soon as we turned on the partial adaptation, that there's already an improvement in what's going on here. And this will become more apparent. Moving forward in time, you see as the set point has been changed over a wide operating region, that the control is ideal at each point of operation. This is because the tuning has changed as the state perimeter changes from one region to another in conjunction with the approved the tuning rule to give you the proper tuning for each point of operation. Now with adaptation, you can also go to full adaptation. The difference between partial and full is the fact that with full adaptation, as the state perimeter moves from one region to the other, you immediately shift to the model that was approved, but then allow the model then to be adapted as new models are identified. The adaptation is limited to an approved range of operation of dead time, time constant, and gain. Therefore, you don't have to worry about it adapting to a region that would be invalid just due to maybe some abnormal operating condition in the plant, like a shutdown of the loop or something. I hope this example has been helpful to you in understanding adaptive control.